Hey everyone, welcome to this explainer. Uranium is one of those words that instantly sparks a ton of curiosity and, quite frankly, sometimes a little bit of fear. We constantly hear about it in the news connected to nuclear energy, atomic weapons, and even those wild science fiction stories about radiation. But what exactly is it? Today I want to invite you on an engaging journey to really understand what is arguably the most powerful element on Earth. We're going to map out the profound tension between human progress and human caution, relying strictly on the facts, the history, and the science.
So here is our roadmap for today. We'll be covering the heaviest element, a glowing accidental history, the science of splitting, fueling the modern world, weapons, war, and waste, and finally, mining the future.
All right, Section 1, the heaviest element, a 92-proton behemoth. Okay, let's dive into this. Uranium sits on the periodic table as a naturally occurring element packed with 92 protons.
And because of all those protons, pure uranium metal is incredibly, almost unimaginably dense. Seriously, if you were to hold a chunk of pure uranium in your hand, you'd be shocked by how heavy it is. It's roughly 19 times heavier than the exact same volume of water. That sheer massive density is actually our very first major clue as to why this element holds such incredible potential as a source of raw energy.
Section 2, a glowing accidental history, from glassware to radioactivity. Let's rewind for a second and take a fascinating flashback at how humanity first interacted with this stuff, completely unaware of the sleeping beast inside. Back in 1789, a German chemist named Martin Heinrich Klaproth identified it while analyzing a mineral called pitchblende. He named his new element after the planet Uranus, which had just been discovered. But here is the really wild part. For most of the 19th century, scientists had absolutely zero clue about its radioactive nature. No idea. Instead, they actually used uranium compounds to make colorful glassware and ceramics because it gave off this super distinct fluorescent yellow-green color. It wasn't until 1896 that everything flipped. French physicist Henri Becquerel accidentally discovered that uranium salts emitted invisible rays that could actually fog up his photographic plates. That complete accident blew the doors wide open on modern physics, kicking off the study of radioactivity, which was later famously furthered by Marie and Pierre Curie.
Section 3, the science of splitting, unlocking the atom.
Now, what's really interesting about this slide is the breakdown of the element itself. If we zoom all the way down to the microscopic level of this silvery gray atom, we see that natural uranium is overwhelmingly made up of the isotope U-238. That's 99.3% of it. But there is a razor-thin sliver, just 0.7%, that is uranium-235. And that rare, tiny fraction is the whole shebang. It is a fissile isotope, and it's the entire reason nuclear energy is even possible.
So what does fissile actually mean in plain English? Well, it means it can undergo nuclear fission. This is the phenomenon where a U-235 atom literally splits apart when it gets struck by a neutron, releasing an enormous amount of energy in the process. Now, the energy from splitting just one single atom is, pretty tiny on its own. But the real secret to uranium's power is the multiplier effect. When you multiply that single split by trillions of atoms all undergoing fission at once, you get a staggering, almost incomprehensible release of power.
Section 4, fueling the modern world. The bright side of element 92.
And this brilliantly illustrates the mind-blowing math of uranium's energy density. Just think about this comparison. A single, tiny pellet of uranium fuel, literally about the size of your fingertip, can produce the exact same amount of energy as burning an entire ton of coal. It's just wild. That unbelievable density is exactly why uranium is an absolute heavyweight in today's global energy landscape.
But how do we actually get that electricity? The mechanics are surprisingly straightforward. Inside a nuclear power plant, those uranium fuel rods are carefully arranged inside reactors. When the atoms split, they generate a massive amount of heat. That heat boils water to produce steam. The steam drives these giant turbines, and boom, those turbines generate vast amounts of electricity for our cities. The absolutely crucial takeaway here, all of this happens without burning fossil fuels. That makes uranium an incredibly important player in the fight against climate change, giving us a way to produce massive amounts of continuous clean power.
Section 5, weapons, war, and waste, the dark side of fission.
Of course, to truly understand uranium, we have to neutrally acknowledge the immense geopolitical weight and the controversies it carries. Beyond its peaceful uses, it has a much darker reality. During the 1940s, scientists on the Manhattan Project figured out how to harness those exact same fission properties to create atomic bombs. The bomb dropped on Hiroshima in 1945, known as Little Boy, was fueled by highly enriched uranium.
Enrichment is basically the process of artificially increasing that tiny 0.7% proportion of U-235 we talked about earlier, making it suitable for weapons. This single discovery forever changed global warfare and politics. Almost overnight, uranium went from being just another element on the periodic table to a profound symbol of destructive power.
And the severe long-term realities extend well beyond just weapons. Even peaceful nuclear energy produces radioactive waste, and that requires rigorous, careful management for literally thousands of years. On a global scale, uranium sits right at the dead center of intense debates about nuclear proliferation, energy security, and international peace. Plus, there's depleted uranium, the incredibly dense material left over after the enrichment process. Militaries use it in armor-piercing ammunition, which has sparked ongoing debates about the health consequences in conflict zones. And while handling small amounts of natural uranium is actually more of a chemical hazard than a radiological one, inhaling its dust or being exposed to high levels of radiation from its decay products is extremely dangerous.
Finally, Section 6, Mining the Future, the Burden of Responsibility.
So bringing the story back to the Earth, how do we actually extract this irreplaceable yet hazardous material? Let's walk through the global supply chain steps. Uranium is found in minerals right within the Earth's crust, with massive deposits in countries like Canada, Australia, Kazakhstan, and Namibia. First, the ore is mined. Second, it's processed into a highly concentrated powder known in the industry as yellow cake. Finally, it's converted into uranium dioxide for reactor fuel, or it's sent off to be further enriched. Because of the dust and radiation hazards we just mentioned, this whole process requires incredibly strict safety protocols. Protecting workers and preventing water contamination is absolutely critical.
Which brings us to a really pivotal question. How does humanity balance the pursuit of sustainable energy with the intense responsibility of managing radioactive risks? It's an incredibly difficult tightrope to walk, right? On one hand, we desperately need non-fossil fuel innovation to fight climate change and power our future. On the other hand, the environmental impacts and the security risks of radioactive material are heavy burdens that demand total responsibility.
I want to leave you with a final provocative thought straight from our source material that perfectly sums this up. Uranium is truly a metal that has fueled both our brightest hopes and our darkest fears. It is so much more than just a chemical element. It challenges us to balance our highest technological innovations with our deepest human cautions. As we continue to search for sustainable energy solutions, this 92-proton behemoth is for sure going to stay at the very center of the conversation. I really hope this explainer has successfully illuminated the profound duality of uranium for you and maybe leaves you wanting to learn even more about how we manage the most powerful element on Earth. Thanks so much for learning with me today.